Hi, my name is Thomas Kim. This session continues from my previous video, Template Metaprogramming 41, Matrix Chain Multiplication in C++, Dynamic Programming 1/2. And this session is based on Matrix Chain Multiplication Program by Abdul Bari. If you haven't watched this video, please watch it. And because we are continuing from my previous video, if you haven't watched it, please also watch it and download source code from our previous video by clicking this link. Okay, let's get started. This is the previous source code. Click this button, chain product CPP. Enter. And from this file, open it to Ctrl A, Ctrl C, copy all, then paste it here. Now we don't need this file, close it. Here I will remove some files, some functions. We can delete this, the first part, original infix. Then I will remove this. Then instead include talk, play, fun, matrix. And instead of this name, say print order. Fix like this, change like this. Then also change the function name. Once here, twice, then it's done. We will use this function again and again, probably. We will also modify this part. From this file, change the name like this. Build table. We will modify parameters very soon. And we will disable this and this. Create function main. Then here call this function for test build. Copy and paste it here. Now we will build this function. G++, std, C++17. Sorry, it should be equal chain product CPP O GEXE G. The program should build successfully like this. Now here we create a function template. This is element type name element type like this. Talk, play, fun, matrix, element type. This function returns matrix, chain, matrix, product, like this. Then std, vector, talk, play, fun, matrix, element type, MA. Change it to constant like this. It looks very ugly. So we introduce some type names here. Instead of using like this, we will introduce namespace. Namespace matrix chain product, MCP. Matrix chain product. I open the namespace up to this point. Then I will this is end over namespace MCP matrix chain product. Then I will indent like this. Okay, I indent it. Then we don't need this. Here I will define some globals. Constant character pointer NL. Like this. Cout, auto, cout, std, cout. So we defined NL and the cout like this. Then scroll down. We will create a function. Instead of doing this, I will copy this part here. We can actually do like this. Talk play fun. Vector of matrices T element type is identical to this. Okay, so we can modify like this. Talk play fun vector of matrix element type. So we are getting a vector of matrix. First, this has a vector of matrix. Using this function build table, we pass this vector. We pass this vector to this function build table like this. Using table T std using table T, we are defining a matrix. Talk play fun matrix size T. This will be used as matrix for table M and table S. This matrix will be used as type. Then using MS pair T std pair, we are using two table 1, table 2. Okay, this is matrix pair. Sorry, we will copy this part, cut. We will paste it here, and we will also using vector matrices T torque plate vector of matrices. With this, we modify this part like this. ms pair T, and this function takes ms pair T is defined here. Ms pair T is defined here, and this should be template. Type name, element type, constant torque plate vector of matrices, element type MA. So this parameter and this parameter are identical, the same. Here we will create a file like this. We will disable this for the time being. Instead of doing this, we create ms pair T tables like this. In this place we can use like this, auto ms tables. So M will be the first part of pair, the first table. S will be second. We will initialize M and S very soon. I will copy this part like this, and also like this. For your reference. This N5 means the element count of MA. You can say size T, size MA size. We have to plus 1. Because if it is 4 element, then it should be 5. Then here we say size, or we can just say like this. I will modify this part like this, copy, paste, and disable. We modify n size plus 1. This is size is this matrix element count, then I. Okay, this is equivalent. Now we have to build P. How can we build P? We can build P like this is integer vector, so we make like this. std vector size T P, and we reserve P, reserve n, this count n. Okay, then we delete this part. Now we need to build this P element using this MA like this. For auto A MA P in place back ace dim 0. Okay, then here P in place back ace last element, ace size -1. Okay, this dim 1, the last element's dimension +1, like this. Then we will disable this part and test this function. We will disable this part for the time being. And I will delete this function. This function will call this function table build, and it will return, this function will return this pair. Okay, so this is table. Here we return tables. Then we can do like this: auto table M table S build table MA. And in this function we display as cout. No, we will display later. Now we call this function here void test chain product. We call this function from function main. Here using matrix T talk play pun, we will define element type first using element T int matrix element T using vector of matrices T talk play pun vector element of matrix element T. So this is the type, this matrix. Then we make matrix. I copy this. I will create another one. Auto create matrix talk play pun make matrix element T size T size T. Please note that this size, this element, and this table element, tables, this pairs table, this T should be the same. Okay, tables element type. Instead of doing this, I will change like this to make it clear using index T size T to make it identical. This is index T tables, so it should be also index T index T index T here. This should be index T. In this case, MCP matrix chain product. If we do not want to use MCP, then in this function we can say using namespace MCP like this. Then we can use like this index. So this index should be all identical with this tables element type index, and also in this tables index all should be index. Now we create matrix MA we are using this function. This is function cm. We will copy some code from our previous code, chain product, no, test matrix. We will copy this code, this part, like this. They are the same. Now we are calling this function chain matrix product. Chain matrix product MA. Okay. Now let's build and test if it compiles properly. So here we are displaying this P for auto PP P. Cout PP. We are testing if P is extracted properly. Then in command prompt, "46, 46, 46, it should be std. CLS MCP error, A was not declared in this scope. 43, 43. Okay, A is not declared in this scope. Correct. A, MA, then MA size -1. This is the last element, last matrix, column dimension. This is correct. (141). Now let's see 141. 114. This chain matrix, what you saying? So it is complaining anyway here. Return. Let's build once again. Okay. G. Please note that 4, 5, 4, 6, 2, 7 is properly extracted. This number we built 5, 4, 6, 2, 7. Five, 4, 6, 2, 7. This P is properly prepared. Okay. Now in this file, since we prepared the P, now disable this, enable this, and scroll down. Also enable this. Now int should be all changed to index t. Index t. Like this. Copy, paste, paste, paste. Okay. Then another thing, instead of doing this, do like this. Index t. This is unsigned, so we are making big number here. Also this matrix, tables matrix element type is matrix. This is matrix table element. So we have to change, also we have to change like this. Here, parentheses. We are using dynamic array, dynamic matrix. Like this. Change like this. Like this. In this case, we can leave it because this is P is vector. P is simply vector, standard vector, so leave it as it is. And here, modify like this. And also this. Here too. Like this. Now we return table because M and S are actually table members. This is just alias. This is alias. M and S are alias. Then here we built a table, then we can display table like this. See out. Multiplication table M and L. We copy this line once again. This is multiplication order. This is S. I will put label like this. This is matrix M. Multiplication table. This is order S. Okay. Now let's build. This ordered multiplication table and order table should be displayed properly. There is some bug, I think. I size, MD size different. Sorry, we have to create a table. This is declaration, but we haven't assigned dimensions. Table is pair. First table, talk play fun. Sorry, table T. Table T is matrix. We defined table T as matrix, right? So we are using this type declaration like 5. This should be this size n. Okay, so n by n. And the table T n by n. The first is for matrix M. This is for matrix S. This is multiplication table. This is for order table. Then let's try. Okay, multiplication table is built successfully. Then this is order, multiplication order. Now we don't need this. It works perfectly, so we disable this part. We don't need to display now. And also, since table is built successfully, we will disable this part too. Now we have to calculate. This is S is, I will just say M and S. Like this. Now using S, we call this function. We call print order this function like this. Here, std cout, just cout, print order S1 S size S dim 0 -1 like this. Okay, now let's run again. Then multiplication order will be displayed. G++ SED C++17 chain product CPP OGEXE. Let's see. Sorry, we have to modify this. We change it like this. This is table T, constant table T, reference, like this. We modify, and it should be index T. I modified like this, and it also should be changed like this. And also here, then here, let's see, it's done. It's fixed. Now let's run. Okay. Now matrix multiplication order is displayed successfully. Now we are doing real computation. Now copy this part of function, this function, up to this point, copy, paste, change it to chain compute chain product, and we have to change it to index T, and here we are providing, sorry, we need to provide template, type name element type, here talk play fun matrix element type. Please note that this is reference. I would say A. Okay, then talk play fun vector of matrix element type MA. I will make it constant. This will be calculated matrix. Okay, a vector of matrices to multiply. Then we have to change this, copy, paste. Please note that we are making a simple calculation first. This returns matrix, left side of matrix. We don't need this now. We simply do like this. Return. No, this should be matrix. Talk playpen, matrix, element type. This is return value. Return value is a matrix. Then this is left hand side. We compute the left hand side. And we multiply right hand side. Then we return. We have to fix like this. Then here we are actually returning matrix. Return MAH. Please note that this MA is zero-based index. MA is zero-based vector, and this S is not zero-based, it is one-based. So we have to minus 1. We have to subtract minus 1. No, we have to subtract 1 from H, because MA is zero-based. Then it works successfully. Here we have to pass. No, I will disable this part for the time being. I will disable it for the time being. Then it should be MA. We have to pass MA like this. Also here MA. This is left hand side. Left side matrix. This is right side matrix. We are multiplying together. Okay, then we return like this. Then we call this compute chain. This I will name it naive method. Naive method. I will call this function. This function returns calculated result, this result. Then we can call here. It returns matrix. No, we can just return, because this returns matrix. Then here we provide MA, and we are calling this function. This should be MA like this. This function uses this matrix MA and as this table, and computes the matrix multiplication, then returns matrix computed result like this. And here we can display now cout chain multiplication like this. And L. Fifty. Sorry, we have to copy like this. Okay, modified. Let's run again. Something wrong. We created a matrix, but we haven't initialized the element of matrix. I will create a random number generator here using random t talk play fun random t. Then we have to provide element type like this. Then I create random generator here, random t random. We have to provide the range from 0 to 10 inclusive. Random number generator from 0 to 10 ins inclusive. If we want to generate numbers of double, then if we change into double, then it generates random numbers of double. Then here we initialize these elements of matrix like this. For auto A MA A generate. We provide this random, then it generates random numbers of each element of this matrix. Initialize matrices with random numbers. Then we can display like this. Cout A is dim 0, dimension 0, A dim 1. This is low dimension. I will say number of rows. This is number of columns of a matrix. Then we close. Then A and L. Then these are generated. So now we can compute once again. Okay. Voila. So in this here, we generate random numbers and assign to each element of matrix like this. Then we call chain matrix product. Then we display the result. I will put a range like this. Then here we will make a few changes. For example, we can display cout. We can display table. We can now enable it for testing purpose like this. Then let's try once again. We changed the names M, such as MS, S. So everything is done. We dynamically generated 4 matrix and initialized with random numbers, and we built a chain table, multiplication table, and multiplication order table. Then using this matrix chain multiplication method, we computed the result and displayed. To test, I prepared another function in advanced. Simple multiplication talk play fun matrix simple product MA. This is simple matrix product without using chain multiplication method. It just calculates all product conventional way. We can double check. If we compare two matrices, 2 6 3 6 8, 2 6 3 6 8, 2 6 1 17 4, 2 6 1 17 4. See, these two matrices are identical. So this matrix operation works. Matrix chain multiplication works successfully. But this method is very inefficient. I will disable this part, and I will show you one thing why this method is inefficient. Here I give define verbose. If we define and enter and run it, then let's see. This is 4 matrix initially. Initially we created 4 matrix, so this is copy constructor. This is unavoidable. However, if we see there is one move constructor, and 4 copy constructor occurred. 4 copy constructor. Copying from one matrix to another matrix is very expensive operation, because this copy constructor is very expensive. Okay, the problem is here. We are returning a copy of a matrix. We are returning a copy of matrix from MA. Okay, so this is very inefficient. Also here we are also copying the intermediate result. We are returning copy of intermediate result. This method is very inefficient. Copy constructor was called 8 times total, and 2 move constructor. Here let's try with the Microsoft compiler. CL EHSC STD C++17 chain product. Now we have to specify like this. Then FEMEXE. We are trying with the Microsoft compiler. M. In case of Microsoft compiler, copy construct is called 7 times, 8 times. Okay? And move construct is called 7 times. So this is 4 times excluding this. Copy constructor is called quite a lot. This is very expensive. Let's try optimization. This is optimization O2. Optimization command. It takes more time because we optimized. M. It still calls copy constructor 8 times. I said copy constructor is very expensive. This is naive method. So I will optimize this part. This part is the problem. We can optimize like this. I copied, paste, and compute chain product. I will change it like this. I change the function name, copy, paste here, paste here. We are not returning matrix. Okay, we are not returning matrix. Instead, we are returning index. Return index of the matrix. We modified this part. This, and we pass calculation result. This is calculation result. Calculated result. Then the remainder is the same. Okay, I will remove this. Let me see. I will arrange like this. And here at this part we have to fix like this. We have to return now index. This is index. We are now returning index. We are now returning index of the matrix. Then here we introduce talk play pun matrix element type M1. I say A1, A2. We create two matrices like this. Then we catch index T, left, IDX. Then we catch the index. We catch the return value of the index and we pass A1 like this. Okay. Then here index T right IDX, right index, right side of index. Now we call this one right hand side. We provide A2. Here, or this is reference. M1, this is left hand side. Left, we are returning, please note that we are returning size. Size is the size of this matrix, like this. And we need to create size here. Index T or size T, the same. MA size, matrix size. So here this left index, the return value, if this return value is less than size, it means if this return value is less than the index of this matrix, then this index is valid. This index is valid. Then we say MA left index. Otherwise, if it is invalid, then we use A1. Okay? Because it will be calculated. Or M2 right hand index size MA right IDX. It means if this index is right hand side, this index is table index, then we use just matrix. Okay? Otherwise, we use calculated index. This is calculated. With this, we can compute like this. This is the A. Calculated result should be calculated like this. M1 close M2. But I created another function that is more efficient than this. A multiply M1 M2. This is more efficient. Now we return size, this size, okay, for next round of use. We are returning size, okay. If we return size, it means this A1, A or A1, A2 is temporary means is the calculation result. Calculation result. Now I said this is matrix chain product. Now we call this function. This is naive method. This returns matrix. So we define a matrix here. Talk, play, fun. Matrix element type. This is result of the matrix. Then here we pass A. Then we call the rest. This is fixed method. Then we return. It returns index. If please note that this returns index. If this is not size means this count of MA, we can say MA size. It means it failed somewhere. It failed calculation. Assert. False. Failed. Otherwise, we return A. Okay? I need to point out another thing. I need to point out if the matrix is just one element, empty, here, if MA is empty matrix, then we return empty matrix. This is empty matrix. Else if MA size is just 1, then we return MA 0. Okay? Else if MA size equals 2, then return MA 0 times MA 1. Else when the size of when the matrix is more than 2, then this is valid. Like this. Now let's build and run and analyze. Using Microsoft compiler 79, I missed semicolon here. Now build. Okay. Now see, move constructor is light. Move constructor is used 5 times. Now let's count the copy constructor. The first copy, for copy constructor is unavoidable because when we initialize it is copied. So first for copy constructor is unavoidable. First it copied, then moved. Just one. And now let's see. Only 2 moved. Only 2 moved. No more copies. Okay, so copy constructor never occurred, but for the first point, this is for initialization. This is just move constructor. We never copied unnecessarily, just 2 move. And if we try with the GNU compiler, now 2 move constructor. This is also 2 move constructor. I will display the trees, expression trees here. We can display expression tree like this. See out. Calculation, print, order. We can provide like this, copy, paste. Please note that this is a little bit inconvenient, so I will make one function. Overloaded function here. And I will remove this part. Return print order S1 S dim 0 -1 like this. Then here we can fix like this. We can simply remove this part Now let's display calculation order as well. CLS G. So move constructor. I will put end line NL so it used two move constructor, just two move constructor. Okay, let's see here. The calculation starts here, calculation begins here. So just after calculation is started, it used just two move constructor. Why? Because it calculates temporarily it creates empty matrix. Okay, I will show you why. Here it is empty matrix. A1, A2 is empty matrix. Okay. Here this temporary is used once. So this is left hand side, right hand side, right hand side in this call, right side in this call. A2 is used. A2 this is temporary. This is created and used, but this is empty. This is initially empty. When it is used, then the content, the calculated result is copied to this A2 just once. Okay, moved, not copied. This calculation result is moved to this A. Okay, just once moved. And then it is moved another time. This is moved twice. I think this is moved. This is calculated once. The calculation result is used once. Then here it is used once again. This is right hand side. So we use only two move constructor. This is very efficient compared with this method. This is very inefficient. Now let's try the example more interesting, longer. I will copy it from test matrix, longer one. I copy this part. Here. Like this. Then we build again. Now this is the calculation of the 6 matrix. It uses one move constructor, two move constructor. It still uses two move constructor after calculation start. It's probably once created in the left hand side, in this side, once created in this side. So two move constructor is used. Then recycled again and again. This is for display purpose. So we never copy. So this is very efficient method. In this session we implemented this chain multiplication. This function we created. And if you do not want to display verbose message like this message, then we introduce, if you do not want to see the message, bool be show info false. I introduce this. Then we can hide like this. If b show info, and we can hide up to this point. like this. I hope you understand this algorithm. We create temporary here, local variable here, then we pass to this compute chain product, and the result is returned from this function through A. A is modified. If the return value is not size, then it is failed. So this is the way we do calculation. Also, don't forget this part. When the matrix is empty, then we return empty matrix. And if matrix size is 1, then we just return 1. If matrix size is greater than 2, then we return the calculated result. I actually completely developed this library all in library form. I already developed all the things and advanced concept. You can watch my other videos, my previous videos about how to use these metrics, how I implemented dynamic metrics. Dynamic multidimensional is not just for 2 dimension, you can define any dimension, any dimensional dynamic array. Please subscribe to my YouTube channel. Thank you for watching.